Hello everyone, I am Javier Morlana and I am going to present you my work Self-supervised visual press recognition for colonoscopy sequences, a work in collaboration with Pablo Azagra, Javier Civera and José Montiel. Colonoscopies work usually with the camera as the only sensor, and they present low level of robotization as a deep understanding of the images is needed in order to navigate autonomously in the colon. SLAM, Simultaneous Localization and Mapping, are typical techniques applied to the field of autonomous robots that can track the camera pose while performing a 3D reconstruction of the scene. These techniques will bring robotization to colonoscopy, but challenges like occlusions will make it fail. In this context, VPR techniques, visual press recognition, are essential, as it enables from failure recovery. Having a database of previously observed frames, visual press recognition is able to relate the current frame with the images in the database if the current place has already been visited. In the example of the figure, after the system gets occluded, the VPR module is able to relate the next frame with the past frames already seen in the sequence. Thanks to that, SLAM can continue with the reconstruction. In this work, we explore the recent advances in this field and propose the first VPR system trained specifically for the colonoscopy domain, showing the improvement in accuracy and recall with respect to the baseline system. We cast press recognition as image retrieval. For this purpose, we use the network proposed by Radenovic. It is composed of a ResNet backbone, followed by generalize a gem pooling, which performs a weighted average of the activations of each feature map, converting each feature map into a single value. The next stage is an L2 normalization applied to the vector, and the result of all of this architecture is that a forward pass of a query image gets converted into a global descriptor of 2048 dimensions that can be compared between against other descriptors by the inner product. The database is created with the descriptors of all the images already seen in the sequence, and a query is performed by a nearest neighbor search against all the other descriptors in the database. We fine-tune the network for the specific domain of colonoscopies. The network is trained in a Siamese fashion using the contrastive laws. We found tuples composed by a query, a positive example that represent the same place, and 5 negative examples that represent different places than the query. These examples are hard-mined, choosing those with the descriptor is similar to the query. Our data is composed by 5 real human colonoscopies, completely unlabeled. We use 3 of them for training, 1 for validation, and the last one for testing. Manual labeling of those sequences is an expensive task, so we need a tool for generate our ground truth. This tool is ColMap, which is an structure for motion system. This works similarly as SLAM, as it creates a 3D map and locates the camera with respect to it, but it can work non-sequentially and create independent maps. So we perform an exhaustive matching between all the images in a sequence, obtaining independent clusters that share copiability information. This copiability is our training supervision obtained in a non-supervised way. For every query, the positive example is another image from the same clusters than the query that shares at least one 3D point with the query. The negative examples are hard-mined from clusters different than the query, but belonging to the same sequence. To validate our approach, we perform 2 kinds of experiments. The first is a non-sequential press recognition experiment, similar to image retrieval. We evaluate it quantitatively with the mean average precision and the recall at n. We compare against the original model trained in cities and landmarks. In this experiment, we treat the whole sequence as a database, and we perform a search for every image. The goal is to retrieve images that represent the same place than the query, no matter what if they are before or after than the query. In this case, the mean average precision improved by 30% with respect to the baseline. For the recall at n, we use an interframe threshold parameter called d that prevents the frame closer than d to be evaluated. That prevents trivial frames to be evaluated. We observe that our system outperforms the baseline, especially in the case that d is high, showing that our system can retrieve frames far from the query. The second experiment is a sequential one. We grow the database as the sequence is being explored and only allows the system to retrieve past frames, as we would do if we were doing SLAM. In this video, we show the query in the left and the first 33 frames in the right, showing that our system is able to perform short-term relocalization. The D parameter is shown here, showing that these frames are close from the query, but when the sequence revisits the place, The system is able to perform loop closure from frames like 4 minutes ago. So we saw that our system is able to relate frames far in time. The extraction time of the query, a single forward pass, takes about 50 milliseconds, which is suitable for SLAM. Our conclusion for these works are threefold. Firstly, we show that our fine-tuning improves our metrics, showing the benefits of the approach. Secondly, we show that SFN can level places in colonoscopies. And lastly, we conclude that this method can give good candidates for the localization of colonoscopic SLAM. As future work, we consider two lines of research. The first one is to take advantage of the intermediate representation of the network to perform re-ranking. And the second line comprises the use of 3D geometry and camera poses for positive example selection. Thank you for your attention.